basically calculus is the study of the rate of change together with some other properties of functions, right? So we add another topic to review all the major types of functions. And after that, we'll have a look at the important topics related to differentiation calculus and then integration calculus. So that ranges from topic 2 to topic 9. Okay? So today we're going to have a look at the first topic. Review of functions. So in this topic, we'll have a look at first some general concepts, and after that major types of functions, which include linear functions or lines in 2D space, quadratic functions, power functions, polynomial, rational, exponential, and logarithmic functions, and then trigonometric functions and inverse trigonometric functions. So for each of these functions, it's always better for you to know its definition and graph. A graph is the most important thing. If you know its graph, basically you know most of its properties, right? And then domain, range, y and x-intercept, asymptotes, if any, monotonicity, which means if there exists a interval, the function is increasing or decreasing. Parity, which means whether this function is even or odd or neither. Whether it has any period, and how we can do transformations, and inverse of each function, and then related equations and inequalities. So let's have a look at these key points. Okay, first let's have a look at some general concepts. So basically a function is a mapping relationship, right? It maps one set to another set, right? A function is a relation in which no two different ordered pairs have the same x coordinate or first component. For each value of x, there is only one value of y, or fx. We sometimes refer to y or fx as the image of x. Are you clear? So that means if you have one input, there is only one output corresponds to the input, right? You don't have more than one output corresponds to the same input. And usually we can use either this notation here or this notation to indicate a function relationship. And the second one is most commonly used, right? And we can also test for functions using the vertical line test. A graph is a function if no vertical line intersects the graph more than once. So for example, look at the graph on the right, which is actually a circle, right? If you do a vertical line test, if you find two intersection points, then this is not a function relationship, because for the same input here, this is our input, which is x, right? You will have two outputs. In that case, that's actually called a multi-value function. It's not a function. It has another name, which is called multi-value function. So there are two types of functions. If you look at the graph under that, we might have 1-to-1 mapping, right? Which means for every input, you will have only one output, and then for every output, that corresponds to the unique one input, right? That's a one-on-one mapping. This is obviously a function relationship. And we might have many-to-one mapping, which means, of course, for any unique input, you will have only one output, right? But for one output, you might have more than one inputs. This is called many-to-one mapping. But still, it's also a function relationship, right? Because it maps each of the inputs to the unique output, right? So basically, function is just a mapping relationship. And next, some properties of a function. Domain and range. The domain of relationship or the domain of a function is a set of values that x can take, which is a collection of your inputs, right? To find the domain of a function, just remember that we cannot divide by 0 or take the square root of a negative number or take logarithm of a non-positive number. Or sometimes you might also want to consider the constraints from the real world, right? For example, if you have a length, if you have a variable that denotes the length of a room, for example, then that variable cannot be a negative number, right? So sometimes the constraints also come from the real world. And the range of the function or a relationship is the set of values that y or fx can take. So simply speaking, that's the collection or the set of all possible outputs, right? And we have a special name for the function fx equals x. This function is called an identity function. Okay, next, another concept, the inverse of a function versus inverse function. So every function has an inverse, but an inverse of a function is not necessarily a function. So I'll explain why. So first of all, we know a function is 1-to-1 if there is only one value of x for each value of y, right? That's 1-to-1 mapping. Or many-to-1 if there is more than one value of x with the same value of y, which is many-to-one relation, right? But the inverse of a function is actually the reverse mapping relationship. Which is usually denoted by inverse of f here. We use this notation to denote the inverse mapping. Did you get it? So for example, if your function looks like this, it maps set x to set y. So, for example, it maps 1 to a, maps to 2, maps 2 to b. Then, for example, we call this function f. Then the reverse mapping, the reverse direction, which maps a to 1 and b to 2, is the reverse of f, which is denoted by f inverse. So be careful, this does not mean f raised to the power of -1, but if f is the function, usually it denotes the inverse of f. Okay, but the inverse of f is not necessarily function. Can you see why? Because if you look at this graph, for 1-to-1 mapping relationship, of course, its inverse is also 1-to-1, right? So its inverse is also a function. But remember that for a function, it could also be a many-to-one type of function, right? So if you consider this case here, the inverse of these types of functions is a 1-to-many, which means if you consider the reverse direction, every input does not necessarily have one unique output. For example, if you consider C here, the same input ends up with two different outputs, right? So the reverse of this function is not a function. Did you get it? Okay, so that's the concept of inverse of a function. And if the inverse of function is also function, we call that function a inverse function. So be careful with the difference between these two words. Okay, any questions? All right. And if y equals fx has an inverse function, y equals f inverse of x, then the inverse function has the following properties. First, must satisfy the vertical line test. This is obvious because for f inverse to be a function, it also have to have only one output for any input, right? So it must pass the vertical line test. And we also know that the inverse function is a reflection of y equals fx in the line y equals x. So basically, the original function and the inverse of function are symmetrical in the line y equals x. So I'll give you some examples when we review the exponential and logarithmic function, because these two functions are inverse of each other, and their graphs are symmetrical in the line y equals x. So we'll have a look at that later. And also we have the following property. F of f inverse of x. So this means function composition, which is a composition between f and f inverse, which basically means you can use another notation to denote the meaning of this. This also means f of f inverse of x. These two expressions have the same meaning. And on the right side, we have f inverse of f of x. All of them are equal and equal to x itself. You see why? Because we can draw a diagram to illustrate this, right? So suppose f maps the set on left side to right. So suppose we have input x here, and there's a function relationship f. It maps x to, let's say, y. Then we know f x equals y, right? Then we also know the reverse mapping is called f inverse, right? So we have f inverse of y should map y back into x, right? So what is y? Y is fx. Therefore, we have f inverse of fx should equal x exactly, right? So that is this relationship here. So using the same method, you can also prove this one equals x, right? And the domain of the original function is the range of the inverse function. You see that? And the range of the original function is the domain of the inverse function, right? Okay, and a invertible function f is self-inverse if f inverse equals f, which means the inverse function is actually the same with the original function. So in that case, that's a self-inverse function. Okay? Any questions? Okay, if not, let's have a look at some examples to check your understanding so far. Okay? So suppose we have two questions here. A, determine the inverse of the function. Then state the domain and range of the function and its inverse. So I'll give you 2 minutes to consider this question. You can write it down on your notebook, okay? And then after that, we'll have a look at the solution together. You can check your solutions with mine, okay? All right, let's have a look at the solution together. So usually, if you want to determine the inverse of a function, we need to check the domain and range of the original function first, because the range of the original function is the domain of the inverse function, right? So for this function, fx equals square root of x plus 3. We know the domain is x plus 3 must be greater than or equal to 0, right? That means x belongs to the interval from -3 inclusive to positive infinity. And the range is from 0 inclusive to positive infinity. Because if you square root any non-negative number, you will also get a non-negative number, right? So if you know the domain and range of the original function, you also know the range and domain of the inverse function. So we could let y equals square root of x plus 3. So in order to solve the inverse function, we need to solve x in terms of y, right? Because you are trying to map y back into x. So as long as you can solve x in terms of y, then you will have the relationship of the inverse function. So this is not difficult. We can easily see that if we square both sides, we have y squared equals x plus 3. Then we interchange the position of x and y. Oh, sorry. Okay, we do not interchange in this step. So from this step to this step, we solve x in terms of y, right? So x equals y squared minus 3. Actually, this is the inverse function. But usually, we'll use y to denote the dependent variable and use x to denote the independent variable, right? So from this step to this step, usually we'll interchange x and y. So if we interchange the position of x and y equals x squared minus 3. This is the inverse function, right? And y is actually f inverse of x. So you could use either y equals x squared minus 3, or use this notation here. Inverse of fx equals x squared minus 3. This is the inverse function. And we know the domain of the inverse function is the range of the original function, and the range of the inverse function is the domain of the original function, right? You understand? Okay, and if you don't have any question, let's have a look at the next trivial concept, which is the graph of functions. On the graph of functions, usually we have the following terms you need to understand. X-intercepts. There probably have no x-intercept, or one x-intercept, or more than one x-intercepts. So it could be a plural form or a single form. The x-intercept or intercepts of a function are the values of x for which y equals 0, right? Or in other words, the x-intercepts can also be defined as the points of intersection between this curve and the x-axis, right? For example, this point here is a x-intercept, right? And this point here is a x-intercept as well. And y-intercept. Y-intercept is a y-intercept of a function is a value of y when x equals 0. Or sometimes people also define y-intercept as points. These are points of intersection between this curve and the y-axis. For example, this is a y-intercept, right? And this is also a y-intercept, right? So careful, you know the concept here. Next, asymptote. Asymptote is a line that the graph approaches or begins to look like as it tends to infinity in a particular direction. So we'll have another definition of asymptote using limits. So we'll review that concept when we study topic 2. Okay? So here, as long as you know the intuitive definition of asymptote, that's fine. So for example, this line here is a vertical asymptote of this curve, and this is a horizontal asymptote of this curve. And to find vertical asymptote, we could look for values of x for which the function is undefined. And to find horizontal asymptote, we could consider the behavior as x approaches either to positive infinity or negative infinity. And also make sure you should be able to use technology or calculators to solve equations algebraically. So you will have some questions during the test using calculators, right? So make sure you know how to use our calculator. Do you have that at hand? So make sure you have a legible, legit calculator during the exam, okay? So from now on, just try to practice your calculators to solve some questions that cannot be solved manually. Okay.